Hello, everyone, and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion science and engineering. My name is Dhaval, and I would like to introduce our speaker today, Ms. Ayushi Vashistha. She completed her graduation and master's in physics from University of Delhi. Thereafter, she obtained her PhD in physics from the for Plasma Research in India. Her thesis work contributes to the study of laser interaction with magnetized plasma, devising an absorption mechanism for coupling of laser energy directly into the ion species. She completed her PhD in 2022, and since then she has been working with Applied Materials Inc. as a computer-aided engineer. Her current role involves modeling and simulation of low-temperature plasmas relevant in the semiconductor industry. Without further ado, I now give the floor to Ayushi. Thank you very much, everyone, for joining, and enjoy the talk.
Thank you, Dhaval, for the introduction. Hello, everyone. I'm going to present a work which is part of my PhD thesis, and the title of my talk would be Localized Absorption of Laser Energy by a Magnetized Plasma Target. Yeah, so this part, the work was carried out at Institute for Plasma Research, India. And this work was carried out in collaboration with Ayushi Vashistha, and Professor. Talking about laser heating scenarios in a laser plasma, ion heating scenarios in a laser plasma interaction. Whenever we talk about ion heating in a laser plasma interaction, ion heating mechanisms are usually mediated by the electron dynamics. So electrons, being the lighter species, are the first one to respond to the incoming laser, and thereby coupling of laser energy into ions is a challenging task due to the huge mass difference between electrons and ions. So the motion of electrons plays a major role here, and ions follow them under the space charge created by the electron dynamics. But here we propose a mechanism where, with the help of externally applied magnetic fields, we arrest the motion of electron such a way that they are tightly magnetized under the application of externally applied magnetic field, and then we shine a laser whose frequency is very close to the lower hybrid frequency of the plasma parameters. Choosing appropriate density gradients in the plasma, we are able to dump laser energy at a localized point in the plasma. Laser energy first converts from electromagnetic mode to an electrostatic oscillation at a particular point, and there the electrostatic oscillations further break to impart all its energy to the ion species. At this point of conversion, where the electromagnetic energy converts to ion species, correspond to the lower hybrid resonance point. I'll describe this further in my presentation. Some of the technological advancements which led to form the basis of our simulation setup are, first of all, the achievement of magnetic field of the order of kiloteslas in the laboratory, and there have been studies to enhance this magnetic field further to megateslas. Then the development of high power long wavelength CO2 laser facilitated the study of laser interacting with magnetized plasma target. So, but the mechanism I'm going to talk about is not dependent on the laser frequency. So any laser frequency would do. The use of CO2 laser only lowers the requirement of the electrons at that frequency. And then we will choose a plasma density profile in our simulation, which has been observed in some experimental studies on laser produced plasmas. Some of the references of these studies are given here. Talking about the simulation parameter, as I described that we're using CO2 laser, so the wavelength is chosen accordingly. All the length scales and time scales are normalized in terms of the skin depth and the electron plasma frequency. So the normalized value for the laser frequency that we use in our simulation is 0.09 times electron plasma frequency. We are dealing with the non-relativistic intensity of laser, hence E naught is 0.5. In some of our studies, we also use E naught. Then we are using a reduced mass of noise, which is we take in our simulations to be 100, just to make our computations faster. Before I describe the mechanism, I would like to give an overview of laser interacting with a magnetized plasma target. Whenever an electromagnetic wave interacts with a magnetized plasma, there could be different modes of propagation. If the propagation of the laser is perpendicular to the externally applied magnetic field, which is shown by V naught here, is further perpendicular to the electric field of the laser, then we call it an X-mode propagation. If the propagation of the laser is perpendicular to the magnetic field, with the externally applied magnetic field and the electric field of the laser are aligned, then it is O-mode propagation. And in our study, we have chosen X-mode configuration. So we use a plane polarized light which propagates along X. Its electric field is along Y, and its magnetic field is along Z, and the externally applied magnetic field is also along Z. This is a two-dimensional simulation setup. And so we, from x equal to 0 to 500, we assume vacuum in our system. And from 500 to 3000 C bar omega PE, we consider a plasma slab. And laser is suspended in vacuum. So laser is ranges from 0, x equal to 0 to 500. And this is the stimulation setup at t equal to 0. Here is a dispersion curve for X-mode propagation of an electromagnetic wave. And I have divided this dispersion curve into 3 major regions. However, the area of interest for all our simulation is region 1. Region 1 corresponds to any electromagnetic frequency lying below the lower hybrid resonance frequency. Region 2 is marked here as the forbidden band. So any frequency between the lower hybrid resonance to the left hand cutoff so any incident laser between these falling between these two frequency would not be able to interact with plasma and would just be reflected back. Again, for region 3, the frequencies lie between the left hand cutoff and the upper hybrid resonance. And region 3 marks a loud band for any frequency within this range. And any frequency within this range would be allowed to penetrate or interact with the plasma species. But in our studies, we would mainly be focused on laser frequencies lying in region 1 of the dispersion curve. To start with, I choose a laser frequency which is very close to the lower hybrid value, and I would show that we could excite some lower hybrid perturbations in the plasma. So with the help of this animation, one can see that initially I'm plotting here electric field along X and Y in the system. At t equal to 0, we only see some electric field along Y, which is due to the laser. And as time evolves, this laser interacts with plasma, hits the plasma boundary, excites some perturbations in the plasma medium, and gets reflected back. But perturbations inside plasma are still remnant even after the laser has been reflected back out of the simulation. And this can be seen from these plots. At t equal to 0, we only see EY in the system. The dashed line is the laser, is the plasma vacuum phase, and the color plot behind shows the charge density perturbation. At t equal to 500, one can observe that laser hits the plasma target. It excites certain mode in the plasma, and one can see from the zoom view that there are some charge density perturbations in the medium. At t equal to 1000, when the laser has left the simulation box, one can observe these charge density perturbations and the electric field along X, which goes very well with these charge density perturbations. So this way, we can see that some electrostatic perturbations have been generated in the plasma medium. And to characterize this mode, first of all, we take a plasma slab in the bulk plasma. We take a small area and we integrate the divergence and curl of electric fields and plot it as a function of time. So we see that the divergence in the plasma medium increases with time, whereas the curl is still very low. This suggests that the electric perturbations inside the plasma medium are electrostatic in nature. So the mode which is generated in plasma is electrostatic in nature. And when we perform a Fourier transform of this mode, we observe that ion and electron move together with different amplitudes, but the frequency of their oscillation is same. And the frequency of their oscillation matches very well with the theoretical expression of lower Hybrid frequency. So from this, we confirm that the mode excited in plasma is a lower Hybrid mode. Then we move to laser frequencies which lie below the lower Hybrid resonance value. From this dispersion curve, one can see that the allowed band is any frequency which lies below the lower Hybrid value. So we address the issue when the laser close to the lower Hybrid value hits the plasma target. But what about if its frequency lies much below the lower Hybrid value? So here we choose 3 different plasma frequencies. One is 4.093, which is very close to lower Hybrid value. And as discussed, here we observe electrostatic lower Hybrid oscillations in the system. Then we go further up till laser frequency of 0.06 in normalized values. From this plot, we can draw 2 inferences. One is as laser energy goes below the LH value, the penetration of laser inside plasma increases. So for laser frequency of 0.093, only 20% of the laser was able to penetrate in plasma, whereas for laser frequency of 0.06, around 60% of laser is able to penetrate inside plasma. So as we go lower in the dispersion curve, the penetration of laser in plasma would increase. And second is for laser frequency very close to the lower Hybrid value, we saw that electrostatic lower Hybrid oscillations are excited in the system. But as we move to the lower frequencies, one can observe that the electromagnetic energy in the system increases and it surpasses the electrostatic energy, which is shown by the blue points. So at laser frequency of 0.06, laser is mostly propagating as an electromagnetic wave in the plasma. Now, to dump all this electromagnetic energy at a particular point in plasma, we choose a density gradient in a way that laser is initially allowed to penetrate in plasma until it reaches a point where it can no longer propagate inside. So it hits the resonance value, and as one can see that from beyond the resonance value, the laser would encounter a forbidden band. So the laser would not be able to penetrate far inside plasma. That's where all the electromagnetic energy converts into electrostatic oscillations and then further into kinetic energy of ions. Here I'm showing the spatial variation of plasma density gradient and lower Hybrid resonance point along with the changing plasma density. Since lower Hybrid, with the expression of lower Hybrid frequency, one can see that it depends on electron plasma frequency, and hence changing plasma density gradient would change the lower Hybrid resonance point. And with the dashed blue line, I'm showing the incident laser frequency. So the point where the incident laser frequency and omega LH meet, this is where all the conversion from laser energy to ion species takes place. And this can be seen from the graph on the right, that when we plot the kinetic energy of ions at 3 different times, we see that they always peak at the same location. It suggests that there has been a localized absorption of energy by ions in the plasma. To further investigate, we plot the electromagnetic field energy and kinetic energy of ions with space and time. Here, the plasma vacuum boundary is at x equal to 850. One can observe that a part of the laser hits the plasma boundary, a part of it is reflected back. So recall that only for this value of laser frequency, which was 0.06, in normalized units, only 60% was able to penetrate inside plasma, 40% of the laser was just reflected back from the plasma boundary. So this is the 40% of the laser which is reflected back, and this is the 60% of the laser which propagates inside plasma until it reaches a point where it can no longer further propagate in plasma. This is where all the energy is collected at a point and it breaks to give all its energy to the ion species in the plasma here. So from this color bar, one can see that the minimum is given by white and the maximum is represented by black. So at this point, as time evolves, all the field energy goes to zero and the kinetic energy peaks at the max. From this animation here, we can see that laser enters the plasma boundary. So the white curve here shows the plasma density profile. So here, up till a certain point, we have a constant plasma density, and then we have a fall in the plasma density profile. So until the laser encounters a constant plasma density, it very well propagates inside the plasma. But as it goes through a gradient in the plasma, this is where, first of all the electromagnetic energy would convert to electrostatic energy. So all the BZ is converted to EX, and further in time, all the EX again gets converted to the kinetic energy of ions. This can be understood properly from these conversion plots here. So here I'm plotting the energy density. I'm integrating the energies over all space and plotting it as a function of time. So between the solid, to the left of the solid curve is when the laser interacts with the plasma. I'm plotting here the electrostatic energy in the system, the electromagnetic energy, and the kinetic energy of ions. So to the left of the solid curve here is when the laser hits the plasma target. To the right of the solid curve, solid line is when the laser has propagating inside the plasma as an electromagnetic mode. Between the dashed line and the dashed dot line is when the electromagnetic energy converts slowly to electrostatic energy. So one can observe that there's a dip in the red curve, and at the same time, the electrostatic energy peaks up. And beyond the dashed dot line, one can observe that even the electrostatic energy goes down, and that's when the kinetic energy of ions kicks in. So all after the simulation ends, all that energy was there in the field energy has been converted into ion species. From the graph on the right, one can observe that. So here I'm showing the kinetic energy of electrons, ions, total energy of the system, and the field energy. Initially, all the field energy in the system is due to laser. Then a part of the laser interacts with plasma, and a part of it is reflected back from the system. So the dip in the total energy that you see here is because 40% of the laser moving out of the simulation box. But beyond that, one can observe that the total energy of the system is always constant. And one can see that the field energy slowly starts to fall down, and the kinetic energy of ions starts picking up. And after a point, one can see that all the field energy has gone to almost zero, and ions have gained all that energy from the laser. So this finally brings to the conclusion of this work. We observe excitation of lower hybrid oscillations in the plasma medium when laser frequency lies very close to the lower hybrid resonance value. And for frequencies less than LHRF, laser hits the plasma target and it propagates inside not as an electrostatic oscillation but as an electromagnetic mode. This electromagnetic mode then reaches a point where its frequency matches the lower resonance frequency for given plasma parameters. And therefore, the electromagnetic energy first converts into electrostatic energy and then finally into kinetic energy of ions at the resonance point in plasma. So using this, we can very well specify where to dump the laser energy at. First of all, we can choose on how much percentage of laser energy is to be dumped into plasma by choosing a particular laser frequency. Then we can govern at what point do we need the energy to be dumped in. And this can be either governed by choosing an appropriate plasma density profile, or changing the gradients would change the resonance point, and hence one can choose where the energy would be dumped at, or one can use different laser frequency. So changing the laser frequency would change the point where the lower hybrid resonance frequency matches with the laser frequency, and that's how one can choose where all the laser energy would be dumped in plasma. So finally, yeah, these are some of the references. Mostly this work has been published in reference 2 and 3, but these are some of the other references that form up. Thank you all for your attention, and I would be happy to answer any questions.
Thank you so very much, Ayushi, for the insightful talk. We will now open the session for question and answers. While we wait for the question from the audience, I have a question myself. I hope it really doesn't come across as a very basic questions. I saw in several plots that we are not exactly using the frequency, but a fraction of the frequency, cyclotron frequency for heating. Do you mean to say that these are the harmonics of the frequency that you are using to heat, or it's just you are trying to see if we go back, yeah, for example, in this plots as well, if you see the laser frequency, yeah, these values. So this is the actual wavelength, or is it? Yeah. Does my question make sense?
Yeah.
Okay.
Actually, all the frequencies are normalized to the electron plasma frequency.
Okay.
Yeah.
Now I get it.
So this is in terms of the electron plasma frequency, but the actual, if you talk about in actual numbers, we use CO2 laser values for our laser parameters.
Okay. All right. Yeah. Thanks. Yeah. But I just didn't catch this part that you were normalizing the frequencies in your plots. Continuing on that, so we can basically, using a tunable laser, practically penetrate as deep as we want to and heat up ions at very different plasma radius. Is this the message of the talk?
Yeah, so basically from this plot, one can see that as you change the laser frequency, the amount of laser that is going inside the plasma changes. So from here, you can tune on how much of the laser you want inside plasma. And then choosing an appropriate density gradient, one would know that the point where the incident laser frequency would match omega LH, that is where all the energy conversion would take place. That's how one can tune with where to dump the energy and how much of the energy.
Okay, and what about the resultant perturbations in the plasma? Did you have a look at it, or it was beyond the scope of the work?
The perturbations, as shown in this animation here, that majorly, if you look at this point, so slowly, gradually, all the field perturbations would just die out. Some of them would be reflected back in the form of some harmonics. So you see some perturbations here. These are probably the second or the third harmonic of the incident electromagnetic wave. But further, what we have in plasma is only the kinetic energy peaking at a point. We don't have much field perturbations left here after a certain point of time. There would be only some harmonics which would be reflected back from this resonance point, and then there would be some some ions, heated ions at this location.
But yeah, the question comes from there. So for example, even if there is a small electric field perturbation, this could create localized electric fields that can then drive charge separation, create some sort of a new mode that could create instabilities in plasma. That's where I was heading with the perturbation. So have you had was there any possibility to have a look at excitation of, apart from heating the ions, excitation of instabilities which are basically harmful for the plasma stability?
Not really. I haven't looked at, because the amplitude of these perturbations is much smaller as compared to our area of interest. So I don't think these perturbations would cause much harm to the plasma, but I haven't looked at them. Okay, what they do to the plasma afterwards.
Okay, thank you so much. So apparently we don't have questions from the audience. Then I'd like to thank Ayushi for the very insightful talk. Thank you so very much for your time. Thanks for joining us, and we'll see you next time.
Yeah, sure, definitely. Thank you. Thank you so much for having me here. And yeah, it's a great opportunity and good to be part of FusionEPtalks.